All right, everyone, we've gotten to one of my all-time favorite multivariable calculus topics. All right, everyone, we've gotten to one of my all-time favorite multivariable calculus topics, divergence. And in the next few videos, I'm going to describe what it is mathematically and how you compute it and all of that. But here, I just want to give a very visual understanding of what it is that it's trying to represent. So I've got it here pictured in front of us, a vector field. And I've said before that a pretty neat way to understand vector fields is to think of them as representing a fluid flow. And what I mean by that is you can think of every single point in space as a particle, maybe like an air particle or a water particle, something to that effect. And since what a vector field does is it associates each point in space with some kind of vector. And remember, I mean, whenever we represent vector fields, we only show a small subset of all of those vectors. But in principle, you should be thinking of every one of those infinitely many points in space being associated with one of these vectors. And the fact that they're kind of smoothly changing as you traverse across space means that showing this very small, finite subsample of those infinitely many vectors still gives a pretty good feel for what's going on. So if we have these fluid particles and you have a vector assigned to each one, kind of a natural thought you might have is to say, what would happen if you let things progress over time, where at any given instant, the velocity of one of these particles is given by that vector connected to it. And as it moves, it'll be touching a different vector, so its velocity might turn, it might go in a different direction. And for each one, it'll kind of traverse some path as determined by the vectors that it's touching as it goes. And when you think of all of them doing this at once, it'll feel like a certain fluid flow. And for this, you don't actually have to imagine. I went ahead and put together an animation for you. So we'll put some water molecules, or dots, to represent a small sample of the water molecules throughout space here. And then I'm just going to let it play where each one moves along the vector that it's closest to. And I'll just let it play forward here, where each one is flowing along the vector that's touching the point where it is in that moment. So for example, if we were to, go back and maybe focus our attention on just one vector, like this guy, one particle, excuse me, he's attached to this vector, so he'll be moving in that direction, but just for an instant, because after he moves a little, he'll be attached to a different vector. So if you kind of let it play and follow that particular dot, after a little bit, you'll find him, elsewhere. I think this is the one, right? And now he's going to be moving along this vector, or whatever one is really attached to him. And thinking about all of the particles all at once doing this gives a good sort of global view of the vector field. And if you're studying math, you might start to ask some natural questions about the nature of that fluid flow. Like, for example, you might wonder if you were to just look in a certain region and count the number of water molecules that are inside that region, does that count of yours change as you play this animation, as you let this flow over time? And in this particular example, you can look and it doesn't look like the count changes. It's certainly not by much. It's not increasing over time or decreasing over time. And in a little bit, if I gave you the function that determines this vector field, you will be able to tell me why it's the case that the number of molecules in that region doesn't tend to change. But if you were to look at another example, like a guy that looks like this, and if I were to say, I want you to focus on what happens around the origin, in that little region around the origin, you can probably predict how once I start playing it, once I put some water molecules in there and let them flow along the vectors that they flow along, the density inside that region around the origin decreases. So we put a whole bunch of vectors there, and I'll just play it for a quick instant, just kind of let it jump for an instant. And one thing that characterizes this field around the origin is that decrease in density. And what you might say, if you want it to be suggestive of the operation that I'm leading to here, is that the water molecules tend to diverge away from the origin. So the kind of divergence of the vector field near that origin is positive. And you'll see what I mean mathematically by that in the next couple of videos. But if we were to flip all of these vectors, right, and we were to flip them around, now, if I were to ask about the density in that same region around the origin, you can probably see how it's going to increase. And when I play that fluid flow over just a short spurt of time, the density in that region increases. So these don't diverge away, they converge towards the origin. And that fact actually has some mathematical significance for the function representing this vector field around that point. And even if the vector field doesn't represent fluid flow, if it represents like a magnetic field or an electric field or things like that, there's a certain meaning to this idea of diverging away from a point or converging to a point. And another way that people sometimes think about this, if you look at that same kind of outward flowing vector field, is rather than thinking of a decrease in density, imagining that the fluid would have to constantly be repopulated around that point. So you're really thinking of the origin as a source of fluid. And if I had animated this better, a whole bunch of other points should be sources of fluid so that the density doesn't decrease everywhere. But the idea is that points of positive divergence, where things are diverging away, would have to have a source of that fluid in order to kind of keep things sustaining. And conversely, if you were to look at that kind of inward flow, or what you might call negative divergence example, and you were to play it, but it were to go continuously, you'd have to think of that center point as a sink, where all the fluid kind of just sort of flows away. And then that's actually a technical term. People will say the vector field has a sink at such and such point, or the electromagnetic field has a sink at such and such point, and that often has a certain significance. And if we go back to that original example here, where there is no change in fluid density, right? What you might notice, this feels a lot more like actual water than the other ones because there is no change in density there. And if you can find a way to mathematically describe that lack of a change in density, that's a pretty good way to model water flow. And again, even if it's not water flow, but it's something like the electromagnetic field, there's often a significance to this no changing in density idea. So with that, I think I've jabbered on enough about the visuals of it. And in the next video, I'll tell you what divergence is mathematically, how you compute it. Hey everyone. So in the last video, I was talking about divergence and kind of laying down the intuition that we need for it, where you're imagining a vector field as representing some kind of fluid flow where particles move according to the vector that they're attached to in that point in time, and as they move to a different point, the vector they're attached to is different, so their velocity changes in some way. And the key question that we want to think about is if you have a given point somewhere in space, does fluid tend to flow towards that point, or does it tend to flow more away from it? Does it diverge away from that point? And what I want to do here is start kind of closing our grasp on that intuition a little bit more tightly, as if we are trying to discover the formula for divergence ourselves, because ultimately that's what I'm going to get to, a formula for divergence, but I want it to be something that's not just plopped down in front of you, but something that you actually, feel deep in your bones. So a vector field like the one I have pictured above is given as a function, a multivariable function, with a two-dimensional input, since it's a two-dimensional vector field, and then some kind of two-dimensional output. And it's common to write P and Q as the functions for the components of the output. So P and Q are each just scalar valued functions, and you think of them as the components of your vector valued output. And the divergence is kind of like a derivative, where you might denote it by just div, and in the same way that your derivative, you have this operator, and what it does is it takes in a function, and what you get is a whole new function. This div operator you think of as taking in a vector field of some kind, and you get a new function. And the new function you get will be scalar valued. It'll be something that just takes in points in space and outputs a number. Because what you're thinking, the thing that it's trying to do is take in some specific point with xy coordinates and just give you a single number to tell you, hey, does fluid tend to diverge away from it? How much? Or does it tend to flow towards it, and how much? So this is the kind of the form of the thing that we're going for. So here what we're going to do is just start thinking about cases where this divergence is positive or negative or zero, and what that should look like. So for example, let's say we want cases where the divergence of our vector field at a specific point xy is positive. What might that look like? So one case would be where your point, nothing is happening at that point, the vector attached to it is zero, and everyone around it is going away. This is kind of the extreme example of positive divergence. And I animated this in the last video where we have all of the vectors pointing away from the origin, and if you look at a region around that origin, all the fluid particles kind of go out of that region, and that's the quintessential positive divergence example. But it doesn't have to look like that. It actually, you could have something where there is a little bit of movement at your point, and then maybe there's movement towards it as well from one side, and vectors are kind of going towards it, but they're going away from it even more rapidly on the other side. So if you think of any kind of actual region around your point, you're saying, sure, fluid is going into that region a little bit, but it's much more counterbalanced by how quickly it's going out. So these are the kind of situations you might see for positive divergence. Now negative divergence negative divergence, let's think about what examples of that might look like. Divergence of v at a given point, and really it's something that takes in all points of the plane, but we're just looking at specific points. So if the divergence is negative, well, the quintessential example here is that nothing happens at your point, but all of the vectors around it are kind of flowing in towards it. And this is the thing where I animated, where we took this and we flipped all of the vectors and said, there, if you start playing the fluid flow, then the density in any region around the origin, increases a lot. All of the fluid particles tend to converge towards that. That might look like divergence of v in any region around the little bit as you're going. So kind of loosely, intuitively, you have something going on, but nothing in a manner that sort of perfectly balances it. They have that will correspond with, these positive divergences ahead. So here I'm going to talk about the Laplacian. Laplacian. And the Laplacian is a certain operator in the same way that the divergence or the gradient or the curl or even just the derivative are operators, the things that take in some kind of function and give you another function. So in this case, let's say we have a multivariable function like f that just takes in a two-dimensional input, f of xy. So you might imagine its graph as being something like this, where the input space is this xy plane here. So y plane here. So each of the points xy is a point here, and then the output is just given by the height of that graph. So the Laplacian of f is denoted with a right side up triangle, and it's going to give you a new scalar valued function of x and y. So it's going to give you a new function that takes in a two-dimensional input and just outputs a number. And it's kind of like a second derivative, because the way that it's defined is that you take the divergence of the gradient of your function f. So that's kind of how it's defined, the divergence of the gradient of f. And a more common notation that you might see here is to take that upside down triangle, nabla, dot product with nabla of f. So remember, if f is a scalar valued function, then the gradient of f gives you a vector field, a certain vector field, but the divergence of a vector field gives you another scalar valued function. So this is the sense in which it's a second derivative, but let's see if we can kind of understand intuitively what this should mean. Because the gradient, if you'll remember, gives you the slope of steepest ascent. So it's a vector field in the input space of x, and each one of the vectors points in the direction that you should walk, such that if this graph is kind of like a hill on top of you, it tells you the direction you should go to increase your direction the most rapidly. And if that seems unfamiliar or doesn't make sense, maybe go take a look at that video on gradients and graphs and how they relate to each other. So with the specific graph that I have pictured here, when you have kind of the top of a hill, all of the points around it, the direction that you should walk is towards the top of that hill. Whereas when you have kind of like the bottom, a little gully here, all of the directions you should walk to increase the value of the function most rapidly are directly away from that valley, which you might call a local minimum. So let's temporarily get rid of the graph just so we can look at the gradient field here pretty clearly. And now let's think about what the divergence is supposed to represent. So now the divergence, and again, if this feels unfamiliar, maybe go back and take a look at the divergence videos, but the divergence has you imagining that this vector field corresponds to some kind of fluid flow. So you imagine little like water molecules, and at any given moment, they're moving along the vector that they're attached to. So for example, if you had a water molecule that started off kind of here, it would start by going along that vector, and then kind of follow the ones near it, and it looks like it kind of ends up in this spot, and a lot of the water molecules seem to kind of converge over there. Whereas over here, the water molecules tend to go away when they're following those vectors away from this point. And when they go away like that, when you have a whole bunch of vectors kind of pointed away, that's an indication that divergence is positive because they're diverging away. So over here, divergence is positive. Whereas the opposite case, where all of the water molecules are kind of coming in towards a point, that's where divergence is negative. And in another area, let's say it's kind of like the center point, where you have some water molecules that looks like they're coming in, but other ones are going out. And at least from this picture, it doesn't seem like the ones going out are doing so at a faster rate or slower than they are here. This would be roughly zero divergence. So now let's think about what it might mean when you take the divergence of the gradient field of f. So let me kind of clear up the markings I made on top of it here. Points of high divergence, points where it diverges a lot here, why are those vectors pointing away? And if we pull up the graph again, the reason they're pointing away is because the direction of steepest descent is kind of uphill everywhere. You are in a valley. Whereas in the opposite circumstance, where divergence is highly negative because points are converging towards it, why are they pointing towards it? Well, this is a gradient field, so they're pointing towards that spot because that's where anywhere around it, you should walk towards that spot to go uphill. So in other words, the divergence of the gradient is very high at points that are kind of like minima, at points where everyone around them tends to be higher. But the divergence of the gradient is low at points that look more like maximum points, where when you evaluate the function at all of the points around that input point, they give something smaller. So this Laplacian operator is kind of like a measure of how much of a minimum point is this xy. It will be very positive when f evaluated at that point tends to give a smaller value than f evaluated at neighbors of that point. But it'll be very negative if when you evaluate f at that point, it tends to be bigger than its neighbors. And this should feel kind of analogous to the second derivative in ordinary calculus. When you have some kind of graph of just a single variable function, the second derivative, the second derivative of x will be low, it'll be negative at points where it kind of looks like a local maximum. But over here, the second derivative of x would be positive at points that kind of look like a local minimum. So in that way, the Laplacian is sort of an analog of the second derivative for scalar valued multivariable functions. And in the next video, I'll go through an example of that. In the last video, I started introducing the intuition for the Laplacian operator. In the context of the function with this graph and with the gradient field pictured below it. And here I'd like to go through the computation involved in that. So the function that I had there was defined, it's a two-variable function, and it's defined as f of xy is equal to 3 plus the cosine of x divided by 2 multiplied by the sine of y divided by 2, And then the Laplacian, which we define with this right side up triangle, is an operator of f, and it's defined to be the divergence, so kind of this nabla dot, times the gradient, which is just nabla, of f. So two different things going on. It's kind of like a second derivative. And the first thing we need to do is take the gradient of f. And the way we do that, we kind of imagine expanding this upside down triangle as a vector full of partial differential operators, partial x and partial y. And with the gradient, you just kind of imagine multiplying that by the function. So if you imagine multiplying that by the function, what it looks like is just a vector full of partial derivatives. You're taking the partial of f with respect to x and the partial of f with respect to y. Those are the two different components of this vector valued function that is the gradient. And in our specific example, when we take the partial derivative of f with respect to x, what we get, so we look over here, 3 just looks like a constant, so nothing happens. Cosine of x halves, the derivative of that with respect to x, we kind of take out that 1/2. So 1/2, and the derivative of cosine is negative sine, so that's negative sine of x over 2. And sine of y over 2, well, y just looks like a constant, so sine of y over 2 is just some other constant. So in our derivative, we just keep that constant in there, that sine of y over 2. And then for the second component, the partial derivative of f with respect to y, 3 still looks like a constant because it is a constant. Now cosine of x over 2 looks like a constant because as far as y is concerned, x is a constant, so cosine of x is a constant. But then the sine of y has a derivative of cosine, and we also take out that 1/2, so you take out that 1/2 when you take the derivative of the inside, and then the derivative of the outside is cosine of whatever was in there. So in this case, y over 2. And we're multiplying it by that original constant, cosine of x over 2. So still we have our cosine of x over 2, since it was a constant times a certain variable thing, x over 2. So that's the gradient. And then the next step here is to take the divergence of that. So with the divergence, we're going to imagine taking that del operator and dot producting with this guy. So if I scroll down to give some room here, we're going to take that vector, this kind of the same vector, the partial x, and I say vector, but vector-ish thing, partial y. And now we're going to take the dot product with this entire guy. So I'll go ahead and just copy it over. Just kind of copy it over here. And let's see. So we'll need a little bit more room to evaluate this. So here, when you imagine taking the dot product, you kind of multiply these top components together. So we're taking the partial derivative with respect to x of this whole guy. And when you do that, what you get, you still have that 1/2, and then the derivative of negative sine of x over 2, so that 1/2 gets pulled out when you're kind of taking the derivative of the inside. And the derivative of negative sine is negative cosine. So negative cosine, this looks like over 2. Then x, divergence up by this further, because both of these terms kind of look identical, gives us the Laplacian. And in fact, we could simplify this further because both of these terms kind of look identical. But the main point of this video is kind of how you go through that process, where you imagine taking the gradient of your function and then the divergence of that, and that's what the Laplacian is.